Welcome, Chem 222 cadets, to Lesson 39, Gas Chromatography. With Lesson 39, it is the 19th of May. We finally got here. Just a note and reminder, our final exam is scheduled for Tuesday, 26 May at your normally scheduled class meeting time, so 0930 for M34 and 1330 for M67. Today we're going to discuss gas chromatography, also a very powerful separation tool that is used in countless analysis laboratories across the country. Just kind of an application note, for years, all of the doping analysis done with athletes, the method of choice is gas chromatography, interface with mass spectrometry. So obviously, that analysis tool is the preferred method that stands up in legal courts as the, positive identification of substances, restricted substances, etc. So very important technique. Today we're going to just look at the instrumentation of the method, the important things that have to be considered in developing a method to use for gas chromatography. The applications include consideration of variables and options for how we prepare the sample and introduce it, the columns that get used, the stationary phase within those columns, the mobile phase, and an important parameter is how we're going to detect the eluent, the compounds coming off the end of the column. And finally, we're going to look at temperature programming as a means of tweaking the analysis time and getting a separation with excellent resolution in the least amount of time possible. Let's begin by considering the instrumentation contained within a gas chromatograph. Let's get our minds into the correct perspective of when we would want to use GC and when it's best to use HPLC. To use GC, okay, our analyte species of interest, okay, whether it's in a solution phase, it's a liquid, or a solid that's been put into a solution phase. If you can readily get that analyte species up into the gaseous phase without degrading it and at reasonable temperatures, then that substance can be analyzed by gas chromatography. Typically, if you can separate a sample and have the choice of GC versus HPLC, GC is preferred for two primary reasons. First of all, it's a simpler technique to optimize all of the parameters you need to get an effective separation, clean resolution in the least amount of time. It also does not generate waste in the form of organic solvents that have to be either regenerated or disposed of. And I guess there's three reasons. And the third reason is superior resolution. We tend to get much narrower peaks. The band broadening when we do GC as opposed to LC is much less, and so it's much easier to get clean separation of our peaks within a reasonable time of analysis. So for those reasons, if you have a choice of GC versus HPLC, you most often are going to choose to do GC. All right, so fundamentally, okay, once again, this process has to happen. We have to get our analyte species up into a gaseous form. So what kind of parameters do we have to have within our instrumental components? First and foremost, we need to introduce our sample through an injection port. Okay, this is usually with a micro syringe. We drop a very small volume and inject it in a liquid or solution phase. You can do direct injection of a gas as well. That sample gets introduced, the needle penetrates a rubber septum, makes a seal, okay? And then we have to introduce our mobile phase, our carrier gas, which is going to sweep whatever's in the sample onto a column. So practical considerations of things that we need in our instrument. Obviously, if I'm going to get this species up into the gaseous phase, I need heat. So your injector component has to be under temperature control. So you're going to have temperature of the oven under control in the experiment. Okay, then our sample traverses the column. Okay, these are typically capillary columns that are very long, can be as long as 30 meters, and so they are wound up into little circular components, and then the end of the column is here. So just like the ejector port needs to have controlled temperature, so must the oven. So you have temperature of your oven has to be under computer control, and you have to tell the instrument what temperature you want, if you want to change that temperature at any point, etc. Once the components come off the end of the column, okay, so I've done a successful separation. I have different analyte species coming off the end of the column. They need to be detected, so you must have a detector and choose amongst a whole variety of detectors. Okay, you don't want this gaseous component condensing in the detector, so it also has to be under temperature control. And then finally, readout and collection of the GC chromatogram by your computer. When doing gas chromatography, there are decisions that have to be made in order to successfully develop a procedure that's going to provide separation of the analyte species in your sample with consideration of a whole host of things. So starting with in what order and what kinds of things you might need to think about. So starting with obviously the analytical process, goals of the analysis. So we need to know what analyte species of interest are present, what are we trying to look for in that sample. We need to know something about the matrix, everything other than the analyte species of interest. We should know approximately the concentration of our species so that we know if we're doing trace analysis down at parts per million or parts per billion, or are our analyte species a major constituent? So there's a lot of it. Okay, in order for GC to be effective, I need to know the approximate boiling point temperature of my analyte species so I know I can volatilize them, get them up into the gaseous phase under reasonable conditions that the instrument is capable of. And I should be cognizant of if my species have any sensitivities to degradation at high temperatures and where that critical temperature is so that I don't exceed that. The next realm of considerations deal with the sample. And am I going to have to do something to my sample before introducing it into the instrument so that I get an optimal separation and detection of my species at the appropriate limits of detection? So, taking us back to our figures of merit in a separation, we need to know, what is the linear range for this instrument for this analyte species? What is the limit of detection? What is the sensitivity? And the selectivity is being taken care of by the separation. So first question is, once again, my analyte species, is it a major constituent? And that benchmark is usually greater than 0.1% of the sample. Or am I dealing with trace analysis in which I'm at parts per million, parts per billion, or lower concentrations? That's typical of environmental samples if you're looking for pesticides or pharmaceuticals that find their way out into the environment, etc. The other thing that you may need to do in order to correct for any variability in the introduction of our sample as we inject it, we can use an internal standard. that we can ratio our peak areas of our analyte species to that of the internal standard, and that corrects for if there's any variability in the volume of sample that actually got into the column or other things that might have happened. So we can correct for those little difficult things that are impossible sometimes to reproduce within a tight window. The other thing we need to know is if we're dealing with trace quantities of substances, okay, we may want to consider doing solid phase extraction or stir bar sorptive extraction if we, once again, are working at really low concentrations. We'll talk about those later. If we're dealing with volatile components, okay, we may want to carry out a preparation known as purge and trap, where we heat the sample and then we capture the gaseous species that come off. And thermal desorption is another option in that regard. As far as the detector is concerned, we have lots of choices. So once again, it depends on the instrument available, which detectors it has. If you're in the position of purchasing an instrument and having a budget that allows you to choose your detectors, it depends on the analyte species you're going to separate. So the general purpose detector that's the least expensive and it's going to give you a signal for anything that comes off the end of the column is TCD. We'll talk about that later. If you're doing organics, a flame ionization detector is probably your best bet. It's more sensitive for those species. If you're doing anything that has halogenated segments in the molecule or nitrogen, those are very electron withdrawing groups, and an electron capture detector would be very useful. This has the lowest limits of detection, so if you're doing super trace, that might be a consideration. And then we get into our hyphenated techniques where we actually put some form of a spectrometer interface to our GC as our detector. Other considerations, the column. We need to choose the type of column, and when we're doing gas chromatography, it's typically a capillary column. Those are going to give us the best resolution. And these are the different types we can pick from. We'll talk about that in a minute. We could do a packed column. It's going to give us the poorest resolution of any GC technique, but if sample capacity is an issue, we may want to go that direction. When you pick your column, you need to pick diameters, the length of the column, and obviously the stationary phase material. And then finally, when we're doing GC, we have to think about how we introduce the sample to the column. And those options include split, splitless, and on column. And we'll talk about the circumstances under which you might want to do each of those. The first thing we need to think about is if we're doing gas chromatography, we likely are going to want to use a capillary column. They are going to give us the best resolution. So what does a capillary column look like? Well, it's got a metal sleeve on the outside. This little gray area right here is a rigid metal sleeve. And then on the inside, we are going to have some source of our stationary phase material along the inner wall. Okay, and then there's going to be an open section. Okay, there's the opening. We call that the inner diameter, and typically that's 0.1 to 0.53 millimeters. And the stationary phase thickness can be in the neighborhood of 0.1 to 5 microns thick. So that is the typical configuration of a capillary column. They typically are very long, so upwards of 30 meters, and so this is a very thin wire. Obviously, it feels like a wire, so to speak, and so to make its position in the instrument as efficient as possible, we wind the long column along a cage, and then that fits in a reasonable 0.2 meter cavity in the instrument. So what types of columns can we choose from? There's basically three kinds. Wall-coated open tubular. As the name implies, we're looking at a cross-sectional view here. We're going to have the stationary phase liquid coating the inner wall here at a very well-controlled thickness. If we want greater surface area, we might use a support-coated open tubular, in which now we have solid support particles, little silica particles typically. Okay, and we have the stationary phase material of interest on the surface of the silica particles. And if we want to increase surface area further, those particles are going to be porous, increasing the pore structure and the surface area. Porous layer open tubular column, PLOT, in which we have pore structures within our little silica particles that are lining the inner wall. Just to illustrate the effectiveness of capillary columns for a real-world application, you're looking at the chromatogram that results from the analysis of the gaseous components that exist in what we call the headspace of a beer can. Okay, and this separation that you're looking at, these are the components that were detected, and the column that this separation occurred on actually has the fused silica backbone 1 micron thick, and onto this particular column we have a high surface area carbon pore structure, okay, of that thickness right there. And so you can see that when we do gas chromatography, we get clean separations, we get good resolution. I don't know if you remember shapes of peaks, but look at how sharp our little peaks are. They're very narrow in width, and that's why if you can do GC, it's preferred to HPLC, because we traditionally get better resolution and the method is just simpler to carry out. So let's compare the performance of the options that we have with our capillary columns. Okay, first we have the option of what's known as a thin film narrow bore column. As the name implies, the amount of stationary phase coated on the inner surface is a thin film. So there's not a whole lot of stationary phase material there. The configuration of the columns, the inner diameter is a maximum of 0.32 millimeters, okay, and the film thickness is about 0.2 microns thick. The advantages in using a thin film narrow bore column: we get the best resolution of any of our columns. This has to do with a more efficient partitioning in the thinner layer of stationary phase. Okay, it's good for trace analysis when our analyte species are present at very low concentrations. It allows us to do fast separations. We can do separations at lower temperatures, and we can elute high boiling point temperature compounds. The disadvantages of a thin film narrow bore column: obviously, since there's so little stationary phase material, we have low capacity. You can easily overload these columns. The detection mode has to be very sensitive, since such low concentrations of species are coming off the end of the column. You need a sensitive detector. So this limits which ones you can use. And they tend to, the silica exposed, once again, has these unreacted silanol sites, and so you have surface activity of the exposed silica because there's just not a lot of stationary phase on the surface. Alrighty, so let's get rid of some of this. Alright, our next type of column is the thick film narrow bore. So as the name implies, it looks like the thin film, but we've got more stationary phase material coated on the inner surface. So these tend to have the same inner diameter as the narrow bore columns, up to 0.32 millimeters, but we have more stationary phase material. The film thickness is 1 to 2 microns. And so how does this perform? What are the major advantages? It gives us good capacity, sample capacity. We can put more sample on the column analyte species at higher concentrations. We get good resolution, not as good as the thin film narrow bore, but still good resolution in the neighborhood of 4,000 plates per meter of column. They tend to be easy to use. They retain volatile volatile compounds. And we can use a mass spectrometer as our detector with these columns. The disadvantages are that it doesn't have as good a resolution as the narrow bore, and the retention times are longer for certain compounds. The final option is a thick film wide bore. As the name implies, we have a thick stationary phase coating on the inner surface. So we have a reasonable amount of stationary phase, and because it's bigger, it's even more than the thick film narrow bore. Dimensions, we're now in the neighborhood of 0.53 millimeters thick. Our film thickness is 2 to 5 microns, so we can certainly put a lot more sample on our column without getting overlap. So we have the highest capacity of any of these techniques. It's good for detectors that don't have our lowest limits of detection, and that's a thermal conductivity detector or an infrared detector. The TCD is the least expensive detector, so these are the better columns to use if those are the only detectors that you have. They're best for your simpler injection techniques, and the downside is they give you the least resolution amongst the capillary columns, so like 500 to 2,000 plates, and longer retention times for higher boiling point compounds. One parameter one has to choose when selecting a capillary column is the length of the column. Commercial vendors will have these available in a variety of lengths, and so it's important to know what additional length gets you in terms of an analysis. So what we're looking at is a separation of a set of 4 compounds on columns of different lengths. So these are identical columns in terms of the stationary phase material, the thickness of the stationary phase on the inner surface, simply different lengths. So one can rationalize what we should get with increasing length of column. As we increase, if you'll remember our discussion of the number of theoretical plates for a separation, number of theoretical plates is equal to the length of the column over the plate height, if you will recall. And so if we increase the length of the column, we should increase the number of theoretical plates. If you will remember, resolution is proportional to the square root of the number of theoretical plates, which is the square root of the length of the column over the plate height. So the resolution of a separation is proportional to the square root of the length of the column. So as we increase length, we increase theoretical plates, and we enhance resolution in terms of a square root of the length of the column as a mathematical function. So we're looking at real data here for separations on analogous columns. The only variable for these columns are their length. So in separating the compounds designated here in the figure caption, we're looking at what happens for a 15-meter column versus a 30-meter versus a 60-meter. You will notice with the 15-meter, we have poor resolution of peak 2. We're not getting baseline resolution. Okay. If we go to the 30-meter column, it's getting better. I'm not quite down to baseline with peak 2. Okay, however, if I go to a 60-meter column, notice that I get good baseline resolution for all 4 components in this particular separation. Obviously, a column of greater length will cost more money, but that may be the appropriate trade-off if you require that level of resolution. Another parameter you must select for your capillary column is the inner diameter. So one might want to consider the impact of a separation in selecting that inner diameter. As we've mentioned before, the inner diameter of the column relates to the resolution. As we decrease the inner diameter of the column, okay, that tends to cut down on the options of partitioning, and therefore it tends to minimize the bandwidth. And if it's minimizing the bandwidth, it's maximizing the number of theoretical plates, which is going to give you enhanced resolution. Okay, real data that demonstrates this relationship. We are comparing the separation of these 4 compounds. On identical columns, the only difference in the columns is the inner diameter metric. So the first one is a 0.32 millimeter inner diameter, so bigger than the one to the right, the 0.25 millimeter inner diameter. And you will notice that peak 2, once again, has very poor resolution on the wider inner diameter column. But if you narrow that down, we're getting improved resolution of peak 2. It's almost coming all the way back down to baseline on the left side here. So you can see clear improvement in that. And so the inner diameter is another parameter that has to be considered in purchasing your capillary column. The other consideration is the amount of stationary phase material coated on the inner surface of your column. So that has to be considered in purchasing and the options therein. So once again, if we want a clean separation, here's the surface of the silica support, and we have coated on the surface of the silica support our stationary phase. And within that stationary phase, there are so many parking spaces, right? And so to get separation of different molecules, each molecule has to have an opportunity to partition in and out of the stationary phase so that we exploit the tiny little differences in time that different structures would spend in the stationary phase and get the separation. If we don't have enough parking spaces, that is enough stationary phase material, we run the risk of not getting a clean separation. So what you're looking at with real data and real chromatograms, to the left, we have a separation of a sample containing those components completed on a 0.25 micron thick stationary phase capillary column versus that of a 1 micron thick capillary column. You can see for the column with less stationary phase material, we are not getting good baseline resolution of most of the components. Our bands are broad, so we are not getting clean separation at the benchmark. Remember, resolution's got to be bigger than or equal to 1.5 in order to have that minimum baseline resolution. With the column that has the thicker film of stationary phase, all 7 components are coming off cleanly with good baseline resolution. And a final note on column selection: although capillary columns are superior in terms of resolution, if capacity is an issue or your detection mode is limited, You can use packed GC columns. The advantages, obviously, packed columns are going to give you greater sample capacity at the expense of reduced resolution. Shown here is an actual separation carried out for a sample and on a packed column. Okay, and it just to demonstrate that yes, you can get a good clean separation for certain compounds using this choice of column. The bands are noticeably wider. Okay, on a packed column, your effective bandwidth down here, much bigger. So once again, that has to do with the fact that the packed column, silica particles onto which a stationary phase material has been chemically bonded, you're just going to get different flow patterns through a packed bed, the eddy diffusion, and then you've got the longitudinal diffusion in the opposite direction to the mobile phase flow, and then just the general mass transfer into and out of the stationary and mobile phases, which tends to make our peaks broader. So moving on, an additional parameter that has to be selected for your capillary column is the chemical nature of the stationary phase material that you're going to have present on that inner surface of the capillary column. So how we choose the correct stationary phase has to do with the polarity of the analyte species we're trying to separate. So just a general knowledge of where certain functional groups sit in terms of polarity, nonpolar substances. You can look at the list here. Weak, intermediate polarity, ethers, ketones, aldehydes, etc. Strong intermediate polarity, so now we're getting into alcohols, carboxylic acids, and then finally strongly polar groups are those here. In terms of stationary phase materials, we're looking at the most common selected types of stationary phases that are purchased with capillary columns. Okay, they're polymers that have been bonded, chemically bonded to a silica surface, and starting with, in terms of polarity, the least polar that we would use for our nonpolar and intermediate polar solutes. We are looking at diphenyl dimethyl polysiloxane. So you've got phenyl groups bonded onto some of the silica atoms, and then we've got methyl groups. So methyl being nonpolar, phenyl being slightly more polar due to the benzene rings. The next option is to have an intermediate polarity. Okay, so these are our cyanopropyl, phenyl, dimethyl polysiloxane stationary phases. So we've got, like the previous one, the two methyl groups, nonpolar. We've got one phenyl group, and now we're going to substitute something that's got more polarity, a cyano group. So remember, carbon triple bond to nitrogen. Nitrogen's electron withdrawing, so this is going to be electronegative this way and this way. So that's going to be a more polar entity on the stationary phase surface. So it's better to be used to separate analyte species that are in that intermediate polarity range. Then we move to strongly polar analytes, in which we want to potentially consider carbowax as our stationary phase material with oxygen in that structure, making it polar. Or we could also choose for strongly polar analyte species the bis cyanopropyl phenyl cyanopropyl groups. So in this structure we've got two cyano groups on this silica, one on this one, and just one of our benzene rings that has the less polar character. One aid in selecting the stationary phase material and its polarity is the retention index. These values are compiled for straight chain alkanes on specific stationary phase materials, and so the values are relative to what a pentane or a hexane or a heptane molecule would exhibit on a particular stationary phase material. So in terms of which stationary phase might work best, let's look at the separation of a mixture of analyte species having the demonstrated boiling point temperatures. To the left is the separation that would occur if we are using as a stationary phase material a very nonpolar polydimethylsiloxane. You will notice that the order of elution of these components is pretty much on the basis of their boiling point temperatures, which has to do with the size of the molecule and the strength of the intermolecular forces based upon those kinds of interactions. If you look at the analogous separation on a strongly polar stationary phase column, polyethylene glycol, columns having everything else held constant, the thickness of the stationary phase, the inner diameter of the column, and the length of the column. So now we are getting separation in which pentanol, probably the most polar, is coming off last as predicted. 6 is butanol, an alcohol, also coming off second longest, etc. So the basis of the interaction with the very polar stationary phase has to do with hydrogen bonding, yielding the longest retention times, and then you have dipole interactions. The polar molecules are coming off intermediate, and then those that only experience dispersion forces are the ones that are coming off fastest. The next parameter that has to be considered and selected is the mobile phase carrier gas. The most typical gases used are nitrogen, helium, and hydrogen. To consider which one might be best in a GC separation depends on the detector you're going to use, and it also requires consideration of the optimal flow rate. We want separations to occur fairly quickly, so higher flow rates usually tend to more efficient separations. So we're looking at Van Demeter plots comparing nitrogen gas to helium and hydrogen. So remember, for optimal resolution, you want the plate height, the band broadening, the measure of band broadening to be minimized. So the optimal flow rate for nitrogen is about 10 centimeters per second, whereas for helium, it's about 23-ish, and for hydrogen, it's about 35, so a much higher flow rate. And notice that the plate height doesn't change all that much for hydrogen over a wide range of flow rates. So for that reason, we get essentially similar resolution and faster flow rates, velocity of the mobile phase, okay, without penalty to the resolution. So we get good resolution and a much broader range of flow rates for hydrogen versus helium versus nitrogen. Once again, you may have to consider the detection mode as well, but for most applications, you're going to want to use helium or hydrogen. This slide demonstrates the actual resolution and separation of a sample containing two components using different mobile phases. All things being held constant, we're looking at the separation first, using nitrogen as our carrier gas at a flow rate of 10 centimeters per second. Okay, we are not getting baseline resolution, and our resolution is 0.87 for these two components. If we had elected to use helium at a faster flow rate, 32 centimeters per second, we are very close to resolution, 1.44 as opposed to 1.50, so close to a clean separation. And most ideally, had we elected to use hydrogen as our carrier gas, okay, using a much faster flow rate, 60 centimeters per second, we have a nice, good, clean separation with a resolution of 1.78. The next consideration for our separation using GC is how we're going to introduce our sample into the instrument and volatilize our components. And this traditionally is carried out by getting your analyte species of interest into some form of a solution or liquid, into which we can use a microsyringe to draw up a portion of our sample. It is optimal to withdraw first a slug of the solvent that you're using to dissolve your sample. So being a solution, obviously there is some solvent that we have elected to place our analyte species into. So you want to draw up first some air, then a little plug of solvent, more air, and then your sample. This order of components will allow your sample to enter the injection port, volatilize, and then any traces of the sample in the barrel will get carried down by the solvent as it gets ejected onto the column. The other consideration is the injection port within the instrument. Most GC instruments are going to allow you to choose to carry out your injection as split or splitless. This has to do with whether or not we allow all of the sample in whatever volume you injected using the syringe. Will all of that sample get to the column or not? So to have the control over how much sample actually gets onto the head of the column, one has an injection port. And so as the design shows, your carrier gas is coming in here. We dry it through sieves, make sure there's no water. We don't want any hydrogen in there, have a trap for that. We don't want any oxygen in there, there's a trap for that. And then we have to control the flow rate. So we have to have a pressure regulator and the flow controller. Okay, this is going to establish whether we're allowing all of the sample to hit the column or not. We have vents here and here. Okay, your sample comes in, you inject your sample here, this little slug of sample gets into the injection port, it's heated, it will volatilize, it will fill this space. This is a mixing chamber, and then eventually that sample is going to obviously vaporize into the gaseous phase and be carried down onto the column. So with the injection port and the computer control of that injection port, you have to alert the instrument as to whether you're going to run the analysis split, splitless, or on column. So if we are doing very high resolution work using narrow bore columns, okay, we have to limit the amount of sample that is carried down onto the column because we have very limited stationary phase material and we will not get a clean separation if too much sample is carried down. So if we're doing trace analysis using a narrow bore column, we want to run our separation and our sample introduction in the split mode, split injection. So basically, if we're running split, that means somewhere in the range of only 0.2 to 2% of the injected sample will actually reach the column. You can program through your software in your computer. You can tell the instrument what split ratio you want. Do you want only one part in 50 to get onto the column? Do you only want one part in 600 to get onto the column? That all depends on the concentration of your analyte species in the sample and the nature of the column that you're carrying out your separation. When you do split, the way this is operationalized, so if we have a flow rate of 102 mils per minute coming in, but only 1 mil per minute coming out, the split ratio there is pretty close to 100 to 1. So what that means is only one part in 100 will actually get carried down onto the column. The rest will get purged through that vent. You can run the injection splitless. Okay. When you want to do splitless is when your sample components are present at very low concentrations and you want all of the sample to hit the column. And the other option is an on-column injection, in which you'll notice that the needle, okay, in the previous cases, the needle only penetrated this far, and so whatever solution there was, okay, is going to hit the injection port and vaporize here, hopefully get that analyte species up into the gaseous phase in the volume here. But in direct on-column injection, the needle's penetrating all the way down to the column. So whatever's in that needle is going to sit on the head of the column. So if it's in a liquid form, it's sitting on the column on a liquid form. If it was gaseous, it's sitting on the head of the column in the gaseous form. This is a way of kind of pre-concentrating your sample and allowing it through the temperature. Remember, we're controlling the temperature of the column. So if that's a high enough temperature, if this is in solution, it will vaporize. Okay, but it's happening at the head of the column, and that can be advantageous sometimes in a manner of pre-concentrating the sample. To demonstrate the chromatograms that would come out if you run a sample split versus splitless, the following diagrams will show this impact. Okay, if you run your separation split, only a portion of the sample hits the column. We're not overloading the column and the fixed amount of stationary phase available. So notice in this two-component mixture, the solvent comes through first, it elutes first, followed by our two components. They're coming off in pretty good time and obviously very clean separation. So we have not overloaded our column by running it split. Had we run the same sample with our split vent closed, that means all of the sample hit the column. Notice that we have very broad peaks, and this is indicative of the fact that we have overloaded our column. We have used up all the parking spaces in the limited stationary phase, and so we are unable to discern components that are similar structurally. They're all just kind of coming through at the same time because there's no place for them to go. The stationary phase is fully occupied. The other option is to run the analysis split vent opened, but with a delay after 30 seconds. Okay, so if we run split with a delay, that's going to result in broader peaks than running it split, but still in a reasonable amount of time and much better than had we put the entire sample on the column with split bed closed. And another option is solvent trapping, in which we, as the name implies, we're going to condense the solvent at the head of the column by temperature control and then allow our components to come through later time. If we are doing an analysis in which our analyte components are at the parts per million, parts per billion level, that is called a trace analysis. It is usually to our advantage to pre-concentrate those species at a higher concentration before introducing them into the gas chromatograph. Remember that whatever components come off the end of the column have to be at a high enough concentration that the detector and its limit of detection, its sensitivity, can discern that those species are present. So if we are dealing with trace analysis, a very useful technique is to use solid phase micro extraction. So this is how it works. Okay, we have a syringe that when we press the plunger, we expose this fiber down here. The fiber has attached some kind of stationary phase material. So there's a coating on the surface of the fiber here of some stationary phase. Okay, and you're going to expose that fiber down into your solution. And so your analyte species, if it's somewhat like the stationary phase material, it's going to come into the stationary phase material on the fiber. So it's going to move out of the bulk solution out here that has a big volume, and it's moving into the stationary phase here that has a smaller volume, and therefore the relative concentration is going up. We can actually predict the mass of an analyte species that will arise in this method. Here's the initial concentration of the analyte in the bulk solution. This is the volume of the thin film in the stationary phase here. This is the volume of the original solution, and the K values here are our partition coefficients between the solvent and the stationary phase material. So this predicts the mass of the analyte species in grams, or I'm sorry, in micrograms, that gets deposited on our fiber. This slide simply shows a successful application of solid phase microextraction for trace quantities of nerve agents. Just a timely and appropriate set of samples that you may come across, seeing as how chemical weapons are no longer allowed, and all of the reserves of chemical weapons in the U.S. have to be destroyed by treaty. There is such a location in Pueblo, Colorado. The Pueblo Chemical Agent Pilot Plant is getting rid of munitions that are mustard agent. That facility does not have nerve agent, but Tooele, Utah did, and other locations do as well. An alternative technique for sample preparation of samples in which you have trace components is stir-bar sorptive extraction, very similar to the previous technique. This time we are going to have our little fiber embedded in a stir bar, and you'll find that stir bar here in this picture up here. So you are stirring the solution vigorously in which your analyte species is in this solution, and ideally moving into the fiber in the stir bar. So this works similar to microphase um, the fiber with the microphase extraction, but this just takes it to the next level. The advantage is the amount, the volume of the stationary phase material on the fiber in the stir bar. So this is going to allow more of our analyte species to move into that fiber, and so it's going to allow us to detect down below parts per billion level. And once again, the same equation applies in predicting the mass of the analyte species in micrograms that can be pulled out of a solution in which the initial concentration of that species is designated by C sub 0. Another consideration in sample preparation, if the nature of your analyte species is that they are volatile, one can pre-concentrate those species by what's known as purge and trap. So if you've got your sample down here and it's contained in an oven that we can increase the temperature, anything volatile in our sample will go into the gaseous phase above the solution. Those gaseous components can come up and be trapped into these sorbent materials up here. Once again, pre-concentrating them, putting them into a smaller volume, and then we can take this tube and place it into a temperature control. So put the tube in here. Your analyte species is all pre-concentrated into that tube. If you heat this and let that go into your column, okay, we have pre-concentrated our volatile components and can detect them at low concentrations. So thus far we have selected our capillary columns, the diameters, the stationary phase material, the thickness of the stationary phase, the nature of the stationary phase. We've optimized the mobile phase, and we've optimized our sample introduction in terms of the preparation of the sample and how we're going to inject it on the column. So a final set of parameters that you will need to communicate to the software before you conduct a gas chromatography separation is the temperature of all of your ovens, and then are you going to change the temperature at any point during the separation? If you'll remember in HPLC, we were able to reduce retention times and make our separations much more efficient by doing what we call gradient elution, where we change the composition of the mobile phase as a function of time. So the analogous complement in GC is temperature programming, in which we are able to alter the temperature at which we are separating our components as a function of time. So we are looking at the temperature of our column where the separation is taking place. Okay, we probably want to give consideration to changing that temperature. Once we've gotten certain components off early, we want to encourage other components to come off more quickly if they're hanging out in the stationary phase, so on and so forth. So the same way that we can tweak mobile phase composition as a function of time in GC, we change the temperature as a function of time. So potentially we start at this temperature, we ramp it, hold it, ramp it, hold it, or we may simply want to choose to ramp it at a certain rate or then ramp it at a much faster rate. It just depends on the application. We are looking at a successful separation here of a range of hydrocarbons in which we initially did the separation at a 20-degree C per minute ramp. You will notice the time of the separation under those conditions is well in excess of about 350 minutes. That is a long time for a separation. We can reduce our analysis time to essentially 225 minutes if we ramp at 40 degrees C per minute, and we can get a reasonable separation at 150 minutes if we ramped at 60 degrees C per minute. So that illustrates the power of temperature programming versus conducting the separation isothermally, where we hold the temperature constant throughout the entire separation. Now we move on to our selection of detectors. Two important things to keep in mind. Is the detector going to respond specifically to certain chemical species, or is it general response? Anything that comes off the end of the column will be detected. And then what are the detection limits and the linear range of those components? So options, the least sensitive is thermal conductivity, followed by flame ionization, then electron capture. This is one of our most sensitive and lowest detection limits of all techniques. The thermal conductivity is general response. It will detect anything, whereas flame ionization, they have to be combustible. In electron capture, there has to be some very electron withdrawing group within the structure. And then we get into other specific detection means. So obviously nitrogen, phosphorus, sulfur here, and others. And then we have the hyphenated techniques where we interface our GC with a spectrophotometer, in which not only do we know what comes off, something comes off the end of the column, but we have a full spectrum, and we can do a positive structural identification of what that compound was. Shown in this slide is a nice correlation between our different detectors, along with the stationary phase that is typical for different columns of different diameters. And so one has to consider how much analyte species is coming through and whether or not the detector is able to see, based upon its limit of detection, that quantity of analyte. So once again, if you are looking at how much sample is required to be detected by the specific detectors, okay, the least sensitive detector is thermal conductivity. Okay, you have to have at least this quantity of material coming through in order for that detector to know something is there. Okay, flame ionization is more sensitive. Okay, it can detect 10 to the negative 12 grams of an analyte species. The nitrogen phosphorus, just a little bit better than the flame ionization. And if you'll notice, the electron capture detector, wow, it's super sensitive, very low limits of detection, down around 10 to the negative 14th, as is a mass spectrometer, okay, in which we're doing selected ion analysis. So the decision as to which capillary column you're using has to go hand in hand with which detector you're using, because this is going to dictate the quantity of the analyte species coming through, and the detectors are limited by their limits of detection. A thermal conductivity detector, or TCD, is the most common in GC instruments. They are the least expensive, and they are a general response detector. Anything coming off the end of the column will be detected. So those are all attributes. The downside is the limit of detection is the highest of all detectors. So you have to have an appreciable amount of your analyte species coming out the other end. So compounds all have a known and predictable thermal conductivity. So if you had pure mobile phase gas coming in and flowing over this heated element, Okay, you will have a certain conductivity of the potential applied across that filament. If in addition to the mobile phase flowing through here, now you have an analyte species coming off the end of the column with the mobile phase, the thermal conductivity will change, and that will be sensed by the current generated, and you will get a signal. And the TCD detectors can be designed for use with packed columns in which you've got more substance coming through versus for the open tubular columns in which you have less components coming through. The next most common detector in a GC is a flame ionization detector. That's an FID. It is unlike a TCD, it is not general response. It's only going to respond to substances that are combustible, so it's really good for organics. It is more sensitive than a TCD, so that's an advantage. How it works, you're going to have coming in hydrogen, okay, and at some point you have your eluent coming off the end of the column. So if you have some analyte species of interest, and that particular species is a hydrocarbon of some kind, it likely can undergo combustion, and in that process it's going to form some free radicals that are charged species, such as that, and this is going to be attracted to a negatively charged electrode, and upon contacting that electrode, it's going to cause a change in the current experience between the two electrodes, and that signal is going to be shown as in the chromatogram here. So this is an example of a separation of a variety of organic species using a flame ionization detector. So it's very useful. The one down below is a specific detector for sulfur-containing compounds, and that can be useful in its own accord. Another useful detector for a gas chromatograph is an electron capture detector. This one, an ECD, it's going to deliver unto us the lowest limit of detection at 5 femtograms per second. So that is an incredibly low detection limit, and it's super useful for environmental samples in which your components of interest are present at very trace quantities. It is not a general response detector. It is only going to respond to molecules or polyatomic ions that have certain electron withdrawing groups, electronegative species. Okay, so halogens, group 7, or compounds that contain carbonyls, nitriles, nitro compounds. These are your most electron withdrawing elements. And so how it works, you've got the eluent flow coming off the end of your column here. So your species of interest, if it contains fluorine or chlorine or bromine, okay, these are very electro withdrawing species, so they are going to capture an electron and form a negatively charged species. So we have to actually have in the detector a radioactive source capable of producing beta particles, which essentially are electrons, negatively charged particles. So those are floating around here, ready to be absorbed by any electron withdrawing species in our structure. And once we formed these species and we have reduced the number of electrons in this cloud, okay, then the number of charged species contacting an anode changes, and that causes a change in the detected current, which gives rise to the signal, which is proportional to the concentration of the molecule or species that contains these electron withdrawing groups. So very sensitive, super good for trace analysis, either environmental or biochemical types of samples in which the species of interest has a very low concentration. We're going to end our consideration of the GC techniques by looking at our most powerful ones. If we interface our sample separation tool, a GC, with a spectrophotometer, that is a very powerful combination. When components come off the end of the column, we don't only know that something came off, we have the power to go in and record a full spectrum for that species and match that spectrum against the spectra of known compounds, and therefore we can get positive structural identification of the actual compound that came off at that point in time during the separation. GC mass spectrometers are very prolific in analysis and research laboratories. As I mentioned before, they are the go-to technique that provides important analyses of samples in forensic science and in our doping considerations with athletes and that kind of thing. So the technique is respected and the data stands up in court. A mass spectrometer can be a very sensitive detector. We have very low detection limits, and then once again we have the positive structural identification of the components present in the sample. These instruments are prolific. They're present in many analysis labs. As far as cost is concerned, you're looking at about a $50,000 purchase for kind of a run-of-the-mill instrument. If you have other capacities going into that, then the cost goes up from there. But a very important set of techniques. And last but not least, we can also interface our gas chromatograph with an ICP mass spectrometer. So once again, incredibly powerful because once we've carried out the sample separation, now the ICP is able to decipher based upon elemental analysis which components are present. And so this combination actually gives us the lowest detection limits possible for all elemental methods of analysis. So these instruments are more expensive. They are more so in the greater than $100,000 cost range, but the more powerful techniques are, the more expensive they become. But obviously you can do a lot more with those instruments. So this ends our discussion of gas chromatography, and I thank you for your attention.